We are currently releasing a new version of SIMBA, version 23.01, and I thought I'll make a quick video to explain one of the new features of this release. It's called MultiTime steps solver. But first, let me explain you how the solver of SIMBA actually works. So SIMBA uses a variable time step solver, and we call this variable time step solver the predictive time step. It's a special algorithm that ensures the maximum accuracy while limiting the number of steps. So in SIMBA, on the right hand side here, you can see the simulation loop. Here we have the time step loop, so everything that happens to one time step. And here we have what we call the Newton loop. So this smaller loop here can be called multiple times per time step. So in SIMBA, the power and control systems are solved simultaneously inside the Newton loop. This has one major advantage. The advantage is there are no delays between the power and the control systems. So the SIMBA solver is actually very well suited to the modeling of average value model of converters, for instance. So to illustrate this, a paper has been recently published. This paper was written by engineers from Hitachi in Switzerland, and they have used SIMBA to model a medium voltage DC network where you have megawatt charging converters, electrical cars charging, batteries, and PV system, and upstream AC network. And in this model, there are about, I think, 80 converters, and they all have been modeled with average value models, and it just works fine. And this is because in SIMBA, the power and the control solvers are solved simultaneously, and there are no delay between the two. The issue is in most of the converters, when we use digital control, actually the digital controller works with a fixed period, a fixed sample time. And this sampling time can be very different from physical time constants that are in the system. That's one issue. The second issue is because of the predictive time step solver, it's very hard for us to model some types of control systems like Z-domain transfer functions and models like delays, root mean square, RMS calculations, and DFTs. So today, here I'm in SIMBA, if I take a simple control block, so here we have a buck converter, we have some voltage and current probes, and we take those values and insert them into a C code block like this one. Okay, and this C code block here, this is a digital controller that have been calculated to work at a given frequency. In this case, 100 kilohertz. That's what is written here. And it works. The problem is we kind of trick SIMBA. We have to add a new clock input here that we will run at 100 kilohertz, and inside the code we need to add a little bit of boilerplate to ensure that the actual controller is called every sampling period. So in order to simplify this and to get models that are closer to the reality, we have developed what we call the multi-time step solver. So you can see the multi-time step solver as different solvers that work in parallel and exchanging data during a simulation. So for the user, the only changes is there is a new parameter on all control devices that we call sampling time. And when this sampling time parameter is set, it's very simple. SIMBA will create a new solver that has a fixed time step that will be called every sampling period. And SIMBA will make sure first that the sampled solver is called exactly every sampling period, and that for every sampling event, a time step is performed into the main predictive time step solver. So we are sure that the data that are sent to the controller are correct at a given time step. So how will we change this device and this model? So it's very simple. First, we will remove all of these because we will not need this clock anymore. And into the C code block, here there is this new sampling time parameters. So instead of 100 kilohertz, here we're in periods, so it's about 10 microseconds. Okay, so this block here will be called every 10 microseconds. And inside the code, I can remove this small hack here. I can simplify. I will change the number of inputs like this, and I will here set the number of inputs from 3 to 2 because we don't need the actual output clock here. And I will add this like this, I will connect it like this, and I will connect it like this. Okay, so this is very simple. It simplifies the model. So it works like this now. So for most of the control systems, they still will be calculated inside the Newton loop with the power solver. However, for models that are sampled, they will be called at the end of a time step, is what we see here down below. So we ensure that whenever we call this solver, the data that is sent to the controller will be correct. Okay, and with this approach, there is still no delay from the power solver to the control solver because they happen in the same time step. However, there will be one time step delay from the control solver, or for the sampled control solver, to the power solver. Okay, so this sampling time property can have 3 different values. The first one is auto. So auto is the default value, and what it means is very simple. That means that it will inherit the sampling time of its source device. That's it. And if there is no source device with a sampling time, then it will be synchronized with the predictive time step solver. If we set it to known, that means that there will be no sampling event and we will be synchronized with the predictive time step solver. And finally, you can also, as we just did, define a sampling period that is defined in seconds. Okay, so by default in SIMBA, all the control model are using the auto value. That means that there are no breaking changes for existing SIMBA designs. And if you don't want to use this feature, you simply leave it to auto and it will just work. Okay, so here, if I go back to my design, this controller will be called at 10 microseconds. But this one here, we can see that this signal here that we use to calculate the inputs of my MOSFETs is at 100 kilohertz. Okay, so if we sample this at 100 kilohertz, it will not work. So here, instead of using the sample signal, I will set it to no or known. So basically only the controller will be sampled at 100 kilohertz. And for the rest, we will still use the predictive time step solver. So we will add point basically exactly at the crossing between the duty cycle and the triangular waveforms. So let's see if it works. And yes, it just ran. And now I can look at the output voltage here. And we can see that our controller has regulated the output voltage to 5 volts correctly. Now I want to show you something else. I want to show you the output of my controller here. So I will select the output here, the output of my sampled controller. And I will add it to my, here, to my system. So this is the duty cycle reference that is calculated by our small C code block. And what I want to show you is this, is if I plot the point and I zoom a little bit, I can see that, of course, this signal is sampled, and it's sampled every 10 microseconds. While this one here, it's hard to see, I will zoom maybe a little bit more, but use a way smaller variable time step. So this is why we have called this feature the multi-time step solver. This is because in one simulation, you can have signals that have different steps. And the first application of this is, of course, this digital control, but we have other ideas in mind that we will use in a later stage. So if I go back to my slide, just a few notes. First, 99% of all the control models, they don't require a sampling period, and they can just be used in the predictive time step solver. However, some devices will require one, like for instance a Z domain transfer function that requires by nature to be sampled, or devices like the delay block. Okay. The second note is, since a full time step is calculated at each sampling event, if you use a very small sampling period or sampling time, the simulation time will be longer, because we'll need to add a lot of points. So the recommendation is to use the sampling time only for digital controller. If I go back to my design here, SIMBA will always be smarter than us to determine where in a control system it needs to calculate the points. This is the beauty of the predictive time step algorithm. So if you don't need to have a signal that is sampled, just leave it to auto. Another note that I wanted to add is on the Python module. So basically, the signals now can have multiple time data, and so you cannot use the same code that was used for sampled signals. So I won't go into the details now, but if you're interested, there is a new example that I just added to our GitHub repository. So that explains how to basically use sampled signals with the Python module. You will see it's very simple. And that's it. So we are currently releasing this version. It will be online and published to everybody in the coming days. And if you don't have SIMBA, you can start using it today by simply going to www.simba.io. Thank you and have a good day.